Hello, everyone. Welcome to the first lecture of Unit 5. In this unit, we are going to focus on impacts. And to do that, I wanted to talk and just start with a little observational exercise. I have a number of images, and we're just going to look through them together to really get a sense of what do impact craters and the process of impact cratering look like throughout the solar system. So in this image, we have an image of our moon. And the more you look at it, the more you will be able to see the history of impact cratering on the surface of the moon. I think our eyes are drawn to the dark spots as well as maybe this really light, bright spot. Here we have the impact crater, and then we have these white streaks that radiate in all directions away from that impact crater. This impact crater is one of the more recent impact craters on the surface of the moon. This is Copernicus crater. Very large, spread material out over the moon's surface in long rays. If we look further, we can see more evidence of these kinds of impacts. We see smaller ones here, maybe older. They aren't as bright and they do not radiate as far as Copernicus crater. But then once we start looking for more impact craters, we start to see more circular shapes on the surface of the moon. So these impact craters are circular, but then we also see that these dark spots, they are also circular in shape. And what these are actually ancient impact craters that have been filled in by lava that has covered the moon's surface. And so once we start to get an appreciation for the impact craters on the surface of the moon, we can start to see that they really cover the entirety of the moon's surface. Zooming in to get a close-up of the moon, we can start to see that there are many different craters of different shapes and sizes. Here we have a really large impact crater with a central peak, as well as some tiered or collapsed rims along its edges. And then we see simple craters strewn around the landscape. It seems that no matter how close we look, we can start to see more craters. Inside this large crater, there are small craters. So there are craters within craters. There are larger craters here, but then if we look on the slopes of this hillside, we can even see additional craters there. So literally, the moon is covered in impact craters across various scales of its landscape. It's not just the moon that has numerous craters. We also see craters on Mars. Here is a digital elevation model that has been reproduced to show what it would look like if we were looking out over the Martian terrain. Here we see different impact craters of various sizes, just like on the moon. However, on Mars, we see that these impact craters don't necessarily form bowls. They form more like pans or plates. We see really sharp edges to their rims, and their interiors do not have a bowl shape. They seem to be very flat. This is indicative that the surface of Mars has experienced a great deal of erosion, and that erosion has broken down the crater rim, and erosion and moving of that sediment over the land surface has then infilled those craters. Many scientists have examined these craters, and they believe that their erosion and infilling was evidence of liquid water running over the Martian surface in the past. And so we can actually use craters to learn more about the history of these planets based upon how their shapes deviate from what we would normally expect to see. Here we have craters on the surface of Mercury. Again, we can see various craters of many different shapes and sizes, just illustrating how common this process is throughout our solar system. And then looking out into the outer solar system, here is Saturn's moon Mimas. Again, almost like a golf ball. It is peppered or covered every inch of it with small impact craters over its surface. These are actually pretty large at this distance. I like Mimas though because it has this really large impact crater with a central peak. This reminds me of the Death Star from Star Wars. It's kind of crazy that an actual moon in our solar system represents or appears similar to something that we see from science fiction. It's pretty cool to see that coincidence. Earth has not been immune to impact craters in the past. Here's an impact crater, meteor crater in Arizona. This impact crater is about the size of Neyland Stadium, or I think 2 times the size of Neyland Stadium. So if you've gotten to walk inside the stadium, if you've seen a game, you know just how big that stadium is and what it's like to be in there. Now just think about doubling its size, and you have what would look like meteor crater in Arizona. Just giving you a nice sense of scale. Here's a road that leads out to the crater. And then here's a visitor center and a parking lot. So just a sense of scale that this is a large building with cars, and then this is the size of the impact crater. Craters appear in all kinds of landscapes on Earth. In Canada, there are really old impact craters. These impact craters are so old that Earth's water and erosion have basically worked those craters into the regional drainage basin system, and that these craters actually now fill up as lakes. Here we have 2 impact craters that formed almost simultaneously. And then here we have one crater that has been massively deformed by plate tectonics, but its overall shape has been preserved through this lake. And then here we have a map of craters worldwide. We can see that a number of craters have been found. I think at least over 100 craters have been found, many of which have been found in places like Australia and the United States, but then also in some desert regions like the Sahara Desert in Africa. We'll talk more about the distribution of craters on Earth and what that means. And so thinking about some goals that we have for this unit, first, I want to reiterate that impact cratering is the most common geological process or event that happens in our solar system. It affects more objects than any other phenomenon that can be seen in our solar system. And so that is a natural place for us to start now that we have covered some of the foundational pieces for planetary geology. Something that I was alluding to when we talked about Mars is that the shapes of these impact craters are very predictable. We know a lot about what they should look like in terms of their bowl-like shape. So whenever craters deviate or change from that predictable shape, we can start to infer that something different has happened on the surface of that planet. In the case of Mars, we were able to learn more about its history of water and erosion. And then finally, major impacts have happened in the history of our Earth in the past, and they represent a serious hazard today. So these are some other things that we're going to get into later on in today's lecture. So this starts off Unit 5, and this is a lecture all about the different types of objects that can impact planets. So we're going to talk about asteroids, comets, as well as the physics of impacts. And this fits within our overall course outcome to identify different geologic features on Earth as well as on the planets and explain how they formed. And to do this, I'm going to need you to be able to describe the objects that cause various impact craters. So this is something you should be able to know by the end of this lecture. And then after that, you'll want to be able to explain how shooting stars, airbursts, and impact craters are created by different sized objects. These are all different phenomena that we may or may not be familiar with, and we want to be able to connect those with different sized objects for various planets. Finally, you'll want to be able to explain the possibility of these events occurring on Earth and what they what threats they pose to society. Okay, so first up, we're going to talk about asteroids. Asteroids represent the first group of objects that can ultimately result in an impact. Asteroids, if we remember from Unit 1, are those rocky and sometimes metallic objects that are left over from the formation of our solar system. These objects, they can take all kinds of shapes and sizes. In general, I think they have like a potato-like shape, but they can have very large range in sizes. So we have different asteroids here that are over 100 kilometers, over 500 kilometers. And then we have the asteroid Bennu, which is less than 500 meters, so much smaller. However, when we look at small Bennu, we can see that it is not a consolidated object as one asteroid, but instead it is more of like a rubble pile where we have large objects the size of houses, and then much smaller objects that are stacked on top of each other. And so the composition and what Bennu is made out of is going to look very different from an asteroid like Vesta. And so ultimately, these materials were what was being brought together to form our solar system during its formation. However, this material was sort of left over, and so oftentimes this material is not melted and differentiated. It does not go through that process of becoming differentiated into various layers by density. Instead, it seems to just be sort of a homogeneous rubble pile or a homogeneous sort of conglomeration of the various materials that were left over from the beginning of our solar system. And so what we also talked about was that there were three main populations of asteroids in our solar system. First, we have the main belt of asteroids. Those are labeled in green here. Those main belt asteroids exist between the orbits of Mars and Jupiter. And this is by far the largest group of asteroids in our solar system. After that, we have in red are the near-Earth asteroids. These asteroids do not orbit in between Mars and Jupiter, but instead make their orbits through the paths of the inner planets. So they cross the paths of Earth, Mars, Venus, and Mercury. They're all in orbit around the sun, but they do not have a circular orbit like those of the main belt asteroids. And then finally, we have the Trojan asteroids. The Trojan asteroids, these share the orbit with Jupiter, and they occur in positions that are in front of Jupiter's orbit and behind Jupiter's orbit. So they are going in front of Jupiter and they are trailing behind Jupiter. And they exist here because of a gravitational balance that exists between the gravitational force of the sun in the center, which is very large, and the gravitational force of Jupiter. These 2 points in that dynamic are very stable, meaning that these asteroids very rarely, if ever, leave their positions. And so oftentimes they will be there and they will not end up colliding with other objects or planets because they are so stable, because they're being balanced out by the forces from Jupiter and our sun. Okay, so a little bit more information about the main belt of asteroids. We have their locations are about 2.2 to 3.3 AU. So that is 2 times to 3 times the distance between Earth and the sun. And there are many, many asteroids in the main belt. It is thought that there might be over 1 million objects that are larger than 1 kilometer, which is quite a lot. And those are quite large objects. And there may even be many smaller objects than that. However, just because there are a lot of objects, it does not mean that this place is very crowded. Actually, this is mostly still empty space. You got to remember that the space in which it occupies continues to expand as you get further and further away from the sun. And so even though we have a lot of objects, they still only take up a very small amount of space in that wide gap between Mars and Jupiter. So the implication of this is that spacecraft as we send them out into the outer solar system, they do not need to dodge and weave around these asteroids. They can fly very easily through the asteroid belt without any worry of coming into contact with an asteroid. In fact, scientists actually try to plan their paths through the asteroid belt to create opportunities to get close to these asteroids, to take better pictures of them and learn more about them. For example, when the Cassini spacecraft was making its way out into the outer solar system to visit Saturn, it got close to this asteroid, and this is about as close as it got to any asteroid. So it's very, very far away and very difficult to see. So if you were actually on an asteroid, it would take you months, maybe even years before you would pass by another asteroid that would be close enough to see. Okay, so then this alludes to the famous phrase by C-3PO in Star Wars that it is incredibly difficult to navigate through an asteroid. That is approximately the chances of successfully navigating an asteroid field is 3,720 to 1. That is purely science fiction. It is wrong. It is very easy to pass through an asteroid field. Only in Star Wars is it very, very difficult. So the main belt of asteroids, they do include very large objects. They include dwarf planets like the object Ceres, which is shown here. Ceres is about almost 1,000 kilometers in diameter. So it is classified as a dwarf planet because it has been formed into an object that is equal to or approximate to a sphere by its own gravity. However, it has not cleared the neighborhood of its orbit, so that leaves it as a dwarf planet. It's important to remember that there are no average size for these objects, these main belt asteroids. There are many, many smaller objects than there are larger objects. And if we want to get an idea of just how much stuff exists in the main belt of asteroids, we can actually see that if we were to bring all of the asteroids together, their mass would actually only be 4% of the mass of the moon and 0.05% the mass of the Earth. And so if you're wondering if the main belt of asteroids represents somehow some ancient planet that may have been torn apart or broken to pieces, that is not the case. There isn't actually enough material to form an object that would be comparable to any of the other planets in our solar system. And so really this is sort of leftover material from the time of planetary formation and does not represent a planet in and of itself. Okay, so then that brings us to the near-Earth asteroids. These asteroids are those that cross the paths of the inner planets. And so we see a diagram here showing that there are in fact a lot of these near-Earth asteroids labeled in red. The main belt asteroids are labeled in green, and so we see many of those out here. Over 26,000 of these main belt or near-Earth asteroids have been identified. And it's important to realize that all of these near-Earth asteroids started their journeys as main belt asteroids. So they began in near circular orbits out here past the orbit of Mars, and then took a change in their journey that brought them in through the inner solar system. The reason why they underwent this change was because of Jupiter. Jupiter has such a large gravitational force that it exerts a large control over the orbits of the objects in the main belt of asteroids. And so whenever a main belt asteroid ventures too closely to Jupiter, Jupiter will actually begin to pull on it more strongly, and it will actually start to cause it to deviate from its circular orbit. This will then lead it on to more irregular paths that bring it through the inner solar system. And so once it is on a path through the inner solar system as a near-Earth asteroid, one of two outcomes will generally occur. That object will encounter a planet or our sun, and the gravitational interaction between that near-Earth asteroid and our sun will ultimately change its orbital path, and that could ultimately send it on a path for an impact. A near-Earth asteroid is going to either have its orbit changed by an interaction with another object, or it will impact an object. Ultimately, once it has entered the near-Earth asteroid stage, will continue to be that until it is impacting an object. So finally, we have comets. Comets are these objects that are icy bodies, icy and rocky bodies that are on very elliptical paths, very elongated paths around the sun. They start in the outer solar system, deep in our outer solar system, out past the Kuiper Belt. And as they come in towards the sun, the sun's heat begins to sublimate that material, transitioning it from solid ice into a vapor. And the release of that gas ultimately kicks up a lot of that dust and gas and creates a coma around the comet. And this causes the coma to make the object very shiny because all that dust reflects light. And also that dust trails away by being pushed away by the sun's solar wind. And again, that dust is very reflective, and so it shines very brightly, and we see that as the comet's tail. It's also important to remember that these are also remnants of the time of planetary formation in our early solar system. However, unlike the asteroids that were present in the inner solar system, these are the remnants of planetary formation in the outer solar system. And so they are composed more often of ices and dust-like material. And it's important to also remember that these are very primitive in that they've never gone through that melting and differentiation process because they existed out in the outer solar system. So what is an example of a comet, it being involved in an impact? Well, the example that we most often talk about is that of the comet Shoemaker-Levy 9. This was discovered by two scientists named Shoemaker, last name Shoemaker and last name Levy. And it was labeled 9 because it was broken, over time, it was broken up into various objects. July in 1992, it was observed that the comet was broken up into various pieces as it passed too closely to Jupiter. Jupiter's gravity gave it an especially hard pull, and this caused the comet to break up into multiple different pieces. As those pieces then went around Jupiter, scientists realized that these objects would then come into collision with Jupiter. And so that event ended up happening in July of 1994. So 2 years later, the objects came back and were on a collision course for Jupiter. And so because the scientists were able to see the breakup event happen, they were then able to predict and train their telescopes onto Jupiter for the impact event. And so many different telescopes pointed their cameras at Jupiter for this event. And what they ended up seeing was the train of comet pieces headed in a direct line for Jupiter. And so their speed of impact, they were accelerated by the gravity of Jupiter, and their speed of impact was about 35 miles per second, which is incredibly fast, even for impacts. What ended up happening was that these objects ended up punching holes into the atmosphere of Jupiter, causing large fireballs to erupt on Jupiter in its atmosphere. And these large spots were basically like scars from the impacts of these comet pieces, ended up being about half the size to equal to one size of the Earth's diameter. And so these are really, really large impact scars on Jupiter. The friction that was created due to these objects basically burning their way through Jupiter's atmosphere created massive fireballs, many, many times hotter than the sun. And so we saw these really large fireball blasts in the thermal images that were taken of Jupiter during this impact. And so now we're going to talk more about the impact events and what causes them to occur. So it's important to realize that a lot of things are happening in the impact process. As a object is coming into the atmosphere of a planet or moon, that object is being heated up by the friction that is involved by the object racing past the molecules in the atmosphere. So ultimately, that friction will have a large control on what types of objects ever make it to the surface. And so for our Earth, for example, very small particles, they are completely burned up by the friction that is experienced in the atmosphere. You may be familiar with these as shooting stars. Very small particles, those objects that are smaller than a few centimeters, are completely burned up by the friction that they are experiencing and the heat that is being generated by that friction, and it completely burns them up. And so when you see a shooting star, you're actually seeing a piece of dust or a small object actually burning up in our atmosphere. And to just give you an idea of this, if you take your hands and you rub them together, that's friction, but it's happening at so many more times the speed as well as the objects rubbing up against each other. The middle category here, so when we get to objects that are a little larger, objects that are less than a few meters in diameter, these objects are also heated up to very high temperatures by the friction and the heating that occurs in our atmosphere. That heating can ultimately cause these objects to explode. This is what we would call an air blast. And so these can also happen. However, oftentimes the friction on these objects after any type of explosion, the friction will actually slow the objects down, that they do not have the force to ultimately create a large impact crater. However, they may explode and that can cause damage. And then the largest objects, these objects are greater than a few meters in size. Anything larger than a few meters in size will have the strength and the speed to completely cross Earth's atmosphere. Despite the friction, despite the heating, they will be able to make their way to the surface and form an impact crater. And so as you can see here, there's a number of different things involved. The thickness of our atmosphere or the atmosphere of a planet will have a great deal of control on what size object will burn up and what size object will make it to the surface and form an impact crater. For places like Venus that have a very thick atmosphere, you need a much larger object to form an impact crater than you would for Earth. Correspondingly, objects that might form an air blast may only burn up in the atmosphere like a shooting star. The greater the atmosphere, the more friction and the more heating. Places like Mars, the Moon, and Mercury have much less dense atmospheres. They have much, their thickness of their atmosphere is much thinner. For the Moon, there's almost no atmosphere. And so in these situations, you aren't going to get shooting stars because there's not much friction to burn things up. And so much smaller objects are going to be able to impact the surface and form craters. It's very interesting that on the Moon, they've actually been able to identify micrometeorite impacts. Very, very tiny objects have been capable of hitting the surface of the Moon and forming tiny, tiny microscopic craters. Whereas on Earth, because of Earth's atmosphere, that object would be burned up in the atmosphere and would not form an impact crater. The composition of the object is also important. If the object came from a core of a differentiated protoplanet, that iron-rich layer, it was all broken up, smashed apart over time. If it was very dense, if that material was very dense like iron, it would be very strong. And so we would be able to journey through Earth's atmosphere relatively easily. However, if it came from another part of that ancient protoplanet, or if it was just rocky material left over from the period of planetary formation, that material is going to be much less dense and it's going to be weaker and it's going to have a difficult time making its way through our atmosphere. Also, the entry speed of the asteroid, and these can range from anywhere from 11 to 70 kilometers per second, which is about 25,000 to 155,000 miles per hour. So very fast and a very wide range of speeds. Ultimately, that's going to determine also how quickly the object is able to move through the atmosphere. If an object is moving slower, friction and heating is going to have more time to burn it up or break it up to form an explosion like an air blast. However, if the object is moving really quickly, friction isn't going to have enough time to really work on that object and break it up or burn it up or cause it to explode. And that object will make it to the surface and possibly form an impact crater. So all of these factors really control whether or not we're going to see an impact crater on the surface or if it's going to blow up or form a shooting star. So it's really complicated. I want to take some time to explain all of those variables and the different options that an object can end up experiencing. So let's just briefly summarize what we've talked about, that those really small objects, this small dust, oftentimes completely burns up, and we usually see these as shooting stars. So these objects are really tiny, oftentimes as interplanetary dust particles. Interestingly enough, these objects are oftentimes the leftover remnants from comets that were in orbit around our sun. And so if you had an ancient comet that made its way through the solar system, and over time that comet has been completely broken up or completely burned up by its sublimation getting close to the sun, those particles that were released on its journey in its coma and in its tail are still in orbit. They're still around in the solar system and continuing to follow that ancient path. The Earth comes around every year and crosses the path of that dust that is in orbit around the sun. This is why we can expect certain meteor showers to show up in certain times of the year, or we can have certain meteor showers that are located in a certain part of the sky. It's because those objects are in orbit around the sun in the same place, and we just come around each year and intersect that point. So here's just some images of shooting stars. I hope that you've seen a shooting star before. If the shooting star ever breaks up, it's often called a fireball, in that it's like a burning ball in the sky. Larger objects, as we move into larger objects, you can have medium-sized objects ultimately result in large explosions. They can form soft landings because they have been slowed down by the friction. However, some of these explosions can be very, very devastating. In 1908, there was the documentation of the Tunguska explosion. This happened in Siberia. Thankfully, it was very far from any sort of civilization. The epicenter of the explosion caused the entire forest around this area to be completely flattened. And some estimates suggest that this explosion was about 10 times larger than a nuclear bomb, just to give you an idea of just how large these explosions can be. These explosions have happened in the recent past as well. In 2013, in the area of Chelyabinsk, Russia, out in Siberia, on the morning of February 15th, commuters on their way to work saw a large fireball crossing through the morning sky. At one time, the heat that was generated from the friction caused this meteorite to be 30 times brighter than the sun. And ultimately, it ended up exploding in the atmosphere that produced a massive airburst and shockwave that rippled through the region. Ultimately, this resulted in many buildings being damaged, oftentimes through the result of broken glass. And unfortunately, this led to many injuries because people went out to their windows to look at this large bright light that they could see in the sky. And unfortunately, once the shock wave reached their house, it broke the glass, resulting in many different injuries. So let's get a look at at how large this object was. Here is the size of the Chelyabinsk meteor. It was about 56 feet in diameter. The Tunguska event was thought to be much larger, about 330 feet in diameter. And just for comparison, here's the size of a Boeing 747. Finally, to wrap up our lecture, we have the largest objects. The largest objects are multiple meters in diameter, and these do come into contact with the surface of the planet or moon, forming an impact crater. Best example of these that we can see today is the meteor crater in Arizona. Again, it is about 5 times as large as Neyland Stadium. This was caused by an iron meteorite, so it was a very strong object, was not going to result in an explosion, and then resulted in a very, very large crater. It's really recent, about 50,000 years old, and that's why it's still present and able to study on the surface of the Earth. So what is the most important part of this impact process? We've talked a number of different things like the composition, the atmosphere. Well, when we want to compare different objects, we really need to think about their velocity. In this equation, the equation for kinetic energy, we have energy is equal to 1/2 times the mass of the object times the velocity squared. So ultimately, whatever the velocity is, it's going to be to the second power. So you're going to take that value and you're going to multiply it by itself. Then you're going to multiply it by the mass and then the 1/2. Ultimately, this means if we double the velocity for any object, we're going to end up quadrupling the energy, because we'll take that 2 for the velocity, and then we're going to multiply it by 2 as well to get the energy. So ultimately, velocity has the greatest effect on the overall amount of energy that is released during one of these impacts. And then I want to wrap up with this final video. This video sort of explores what we can do to stop these types of asteroids from hitting our planet.
Something is going to hit the Earth again. There was an impact in Siberia within the last decade that was caused by an object about 20 meters across.
It broke up in the atmosphere and created a big shock wave. It was 10 times the size of the Hiroshima nuclear explosion.
It injured about 1,000 people in the town of Chelyabinsk.
Of course, if you imagine this happening with a greater population density.
The purpose of the DART mission is to take your spacecraft and you ram it into an asteroid to change the orbit so it won't hit the Earth.
We're not just trying to figure out how to deal with what's coming. No, we're actually going to go out there and we're going to try to stop it. Defense is all great, but you do need to score points. Earth gets hit by asteroids and small debris all the time, but most of the asteroids break up in the atmosphere. All of the bigger asteroids have been cataloged, like the dinosaur killers that are 10 kilometers or 1 kilometers plus. At this point, what we're looking for are things that are smaller, that if they were to hit the Earth, they would create a regional impact.
Asteroid impacts that are big enough to cause damage and cause real problems are rare, but the stakes are really high. So the problem in an asteroid impact is that the Earth is going around the sun, an asteroid is going around the sun, and they both want to be in the same place at the same time. It's been over the past 20 years that planetary defense has started to be taken seriously after an impact into Jupiter by a comet in the mid-90s, and this impact into Siberia, I think, also opened a few more eyes. In 2016, the Planetary Defense Coordination Office was set up in NASA to demonstrate that we can do something about an asteroid impact if something is coming in. a nuclear device. For a long time, it has been the only tool that people had considered. But the concern with dispersing an asteroid is that now you have 2 or 5 or 15 things, and the pieces aren't that much smaller. What we want to do is understand those orbits for all the asteroids that might come close to the Earth. Then it becomes a matter of picking the new orbit you want for the asteroid and then changing its speed. If you have 20 or 30 years to do that, then you only need to change the speed by a millimeter a second or less, and then it'll miss the Earth entirely. The purpose of the DART mission as a whole is to test how this technique of a kinetic impactor would work if we ever needed to use it to deflect an asteroid. Didymos is a binary asteroid system, so there's a main body and it has a satellite. We call those Didymos A and Didymos B. By going to a binary asteroid system for the DART mission, the scale is much smaller. Didymos B is moving around only at maybe 50 centimeters a second. So if you change the speed by a millimeter a second, that is pretty easy to measure, given our capabilities.
The awesome thing is our dartboard, because one should have one, with Didymos B on it. Over here, which is this is the main asteroid, and then Didymos B is clearly where everybody hits. It says the counting down to the time we start the spacecraft INT, where the whole spacecraft comes together. So we're very excited. 163 days is a very short amount of time. It's insane. So DART is launching on a SpaceX Falcon 9 rocket in July of 2021. Each one of the NASA missions has, the main objectives. So our most important one is redirect a moon of an asteroid. Our second most important one, change its rotation period by about 73 seconds. Our third objective is on the ground, they're going to spend some time looking at the rotational period and are able to figure out how much we changed the period. And then our last objective is when we're going to hit it, we're going to create a plume. It's called an ejecta, and people want to be able to measure how much that plume helps push the moon along the way. The DART mission is a technology demonstrator for NASA. We're demonstrating not only our first planetary defense technique, we are demonstrating the Next-C ion engine, we're demonstrating the rollout solar arrays, which is basically solar cells on big blankets, and they provide a lot of power to the spacecraft, and they're super lightweight. But the most important one, of course, is SmartNav, and that's what allows us to hit the asteroid. Didymos B is about 160 meters, so about the size of the Washington Monument. It takes us about 12 months to get to the asteroid. We're going at about 15,000 miles an hour, which means that we're going to be going from New York to DC in 1 minute. As we get closer in, about 8 hours out, we turn on all our systems. We're starting to stream pictures back to Earth. The spacecraft is still under ground control, though. And at 4 hours out, we turn it over to the smart navigation system.
All we see is essentially one bright dot that might be about 2 to 3 pixels large, and that's the Didymos system.
All the folks that are going to be in the mock behind me here, they're just going to be listening. They're not doing anything else. And the spacecraft itself is going to control what it's doing, and it's going to target the asteroid.
At 80 minutes out is when Didymos B starts hopping out from behind Didymos A, starting out at 1, 2 pixels.
We're trying to aim for the center, but imagine a center of a dog bone. Where exactly are you trying to get to? So what you're trying to do by SmartNav is trying to create an envelope of what you think this moon might be like. Even though you don't know the shape, parts of it could be completely dark and you don't actually see them. And yet you're still trying to go for the center. It's very hard.
My biggest thing is to test the SmartNav algorithm to death. We use many different asteroid models, run a bunch of simulations, and see that the algorithm performs as we expect it to.
And then it's not until about 2 minutes out that we're able to completely see the whole moon in its field of view.
We have this communication delay of about 1.5 minutes. That time delay for any decision-making process for humans in the loop in real time, especially at the speeds that we're traveling, is essentially impossible.
And then it's going to perform the impact. You're kind of done at the moment of impact. And if you missed it, that's really not good. So yeah, it's going to be mostly terrifying, probably exciting. The reason why I think DART is so incredibly cool compared to other science investigation mission is that you talk to a person on the street and then you say, oh, I'm working on a mission that's going to study the solar wind, and they say, what is that? Wow. But then with DART, it's a very straightforward mission. You feel like you're helping humanity as opposed to, saying that I'm exploring the world around me.
I think if people can go to bed, sleep a little bit easier, without some existential dread that tomorrow they're going to get blown up by an asteroid that, we can't do anything about, then I think that's good too. If we can lower the stress level of humankind, I think that's also worth something.
Do you feel like you are saving the world?
Yeah,
let me just make sure.
Do I retain the rights to the action figures and stuff?
If you like this video, check out.
I really like this video. It shows the possibilities that exist for these really dangerous events that with science and technology that we can find solutions to these possible problems. And it's really fun to be able to witness those possibilities play out. So that is all I have for lecture 1. I think I've got one more video on the next slide, but I'll let you check it out if you are interested. It's all about the impact that caused the dinosaurs to go extinct. And with that, we will see you in lecture number 2 for our unit on impacts.